Let's jump right into this explainer. Today, we're unpacking Dr. S. Hemamalini's parametric blueprint. If you're doing advanced educational research, this is literally the exact foundational architecture you need to rigorously analyze your numerical data.
So to estimate population parameters, things like the mean, mu, and standard deviation, sigma, your data absolutely has to rest on 5 robust pillars. We're talking normal distribution, homogeneity of variance, independence, interval or ratio scale, and random sampling. Think of these as your strict quality control. Homogeneity, for instance, just ensures variance is roughly equal across your groups, while independence guarantees that every single observation stands completely on its own.
But the absolute keystone here, that's the normal distribution. When your data follows this perfectly symmetrical, bell-shaped curve, your mean, median, and mode all sit perfectly right in the center. And because of this symmetry, the data behaves completely predictably. Exactly 68% falls within 1 standard deviation of the mean. That scales up to 95% at 2, and a massive 99.7% at 3 standard deviations.
Now, here is the golden rule you have to remember. If your data seriously violates this normality, you cannot force it. It's just not going to work. You must pivot. You either transform the raw data, or you shift entirely to non-parametric alternatives. We're talking tests like the Mann-Whitney U, Wilcoxon-Sign Rank, or Kruskal-Wallis.
Okay, assuming your data actually meets those strict criteria, the entire territory of parametric tests basically splits into 2 distinct hemispheres. Hemisphere A is all about finding differences, so specifically comparing group means or variances. Hemisphere B, on the other hand, shifts our focus over to finding connections, establishing solid relationships, and building out predictions.
Let's dive right into Hemisphere A, starting with the t-test family. Developed by William Seeley Gossett, who famously published under the pen name Student, these tests are designed specifically for small samples where the population variance is unknown. The first branch here is the one-sample test. This compares a sample mean against a known standard. For example, comparing a B.Ed student competency average of 82 against a strict university standard of 75.
Now, the other 2 branches handle group comparisons a bit differently. An independent or unpaired t-test compares the means of 2 entirely distinct groups, like, say, evaluating male versus female teachers' job satisfaction. A paired t-test, however, measures the exact same group twice. A classic example would be testing trainees' communication skills before and then again after a specific training program.
Let's actually put that independent t-test to work in a real educational scenario, comparing the mean scores of male and female teachers. So imagine we have 35 male teachers with a mean of 55 and a standard deviation of 5, pitted against 40 female teachers with a mean of 60 and a standard deviation of 8.
We can methodically process this through 4 exact steps of hypothesis testing. Step 1 establishes our null hypothesis, basically assuming no significant difference exists. Step 2 is our calculation engine. Running our group data through the formula gives us a calculated absolute t-value of 3.29. Step 3 sets our threshold, using a critical table value of 1.99 at the 5% level. And finally, Step 4 is the verdict. Because our calculated 3.29 completely shatters that 1.99 threshold, we reject the null hypothesis. There is for sure a significant difference here.
Also hanging out in Hemisphere A is the F-test, developed by Sir Ronald A. Fisher, but instead of comparing averages, the F-test compares independent population variances. It's essentially testing for homogeneity by dividing the larger variance by the smaller one. Are we looking at a tight curve with low variance or a wide, highly varied curve? If you're comparing the spread of math achievement scores between government and private schools, you're relying exactly on this test. Plus, it forms the very foundation of ANOVA.
Speaking of which, when we step up to the entire OVA family, we can elegantly map these tests across 2 crucial dimensions. On the x-axis, we just ask, are we controlling a covariant? And on the y-axis, we measure the number of dependent variables.
It's pretty cool how these 2 dimensions entirely dictate your specific test. Got 1 dependent variable and no covariate? That's ANOVA, which compares the means of 3 or more independent groups using the mean square between over the mean square within. Now, if you need to filter out the influence of an extraneous variable, a covariant, you shift to ANCOVA. If you have multiple dependent variables without a covariate, you're going to use MANOVA to test them simultaneously using Wilks lambda. And if you add a covariate back into that complex mix, well, you arrive at MANCOVA.
To really see this matrix in action, let's evaluate a single independent variable, teaching method, comparing lecture, activity, and blended styles. ANOVA simply asks if the method impacts academic achievement. ANCOVA asks the exact same question, but statistically controls for the student's pretest scores. MANOVA broadens the scope significantly, asking if the teaching method simultaneously impacts academic achievement, creativity, and critical thinking. And finally, MANCOVA handles all of those multiple variables simultaneously while still controlling for those pretest scores.
All right, let's cross over into Hemisphere B, where we shift our focus to finding connections. Pearson's product moment correlation, or just R, measures the strength and direction of a linear relationship on a precise scale from -1 to +1. So if X is study habits and Y is academic achievement, a positive correlation just means that as habits improve, scores tend to rise. But always remember the cardinal rule here: correlation does not equal causation.
Building logically from correlation, regression takes us a powerful step further. It acts as our actual prediction engine. Linear regression relies on one predictor, mapping an equation of y equals a plus bx, while multiple regression utilizes 3 or more. By plugging in independent variables, things like study habits, motivation, and attendance, into our equation, we don't just see a relationship, we can calculate a precise, predicted academic score, like predicting a 92 for a specific student.
And this brings us to the ultimate distinction between our two main tools in Hemisphere B. It's essentially the difference between looking through a magnifying glass versus looking through a telescope.
Notice the phrasing here. Correlation is the observer. It acts as that magnifying glass, simply asking, are these two variables related? It focuses strictly on measuring the strength and direction of an existing relationship. Regression, on the other hand, is the forecaster. Operating exactly like a telescope, it looks ahead, asking, if I know X, can I predict Y? It establishes a mathematical equation to estimate exact future outcomes.
Now, let's backtrack just a second. Even if we find a statistically significant difference back in Hemisphere A, we still have to ask a highly critical question. So what? That's exactly where Cohen's effect size, or D, comes in. A t-test proves a difference exists, sure, but Cohen's D reveals if that real-world gap actually matters in practice. Is the effect small at 0.20, medium at 0.50, or is it massive at 0.80? This calculation determines if the difference between, say, activity-based and lecture teaching is practically large enough to actually justify overhauling an entire curriculum.
Bringing this whole journey together, the synthesis acts as your master decision tree. Your primary research goal dictates your tool. Are you comparing means? 2 groups gets a t-test. 3 or more gets a NOVA. Examining variability? Reach for the f-test. Analyzing complex data? Use ANCOVA for covariance and MANOVA for multiple variables. And finally, to find relationships, you either describe them with Pearson's R or you predict them with regression.
And this leads us perfectly to the ultimate takeaway of our explainer today, the true purpose behind mastering all of these specific methods.
Parametric statistics are not just mathematical formulas. They are the precise architectural tools we use to turn raw data into rigorous, actionable educational insights. The question for you is, which of these parametric blueprints will you reach for next to construct your own rigorous discoveries?